Imagine a telephone that can be in only one of two states. It is either free or busy. Every minute it may stay in its current state or switch to the other one. This simple system introduces one of the most important ideas in probability, the Markov chain. The same mathematics is used to model weather, financial markets, internet traffic, queues, communication systems, biological processes, and quantum systems. Let us build the idea from the ground up. Suppose the telephone is currently free. During the next minute, it becomes busy with probability p. It remains free with probability 1 minus p. Now suppose the telephone is busy. During the next minute, it becomes free with probability q. It remains busy with probability 1 minus q. The problem asks two questions. First, what is the probability that the phone is free after n minutes? Second, as time continues, does that probability settle down to a fixed value? In other words, does the telephone eventually reach a stable, long-term behavior? The defining feature of this model is the Markov property. To predict what happens next, we only need to know the current state. Suppose you walk into an office and see that the phone is busy. To predict whether it will be free 1 minute later, you do not need to know what happened yesterday. You only need to know that it is busy now. This is often described as the memoryless property. The future depends on the present state, not on the entire history. A light switch provides the same intuition. If a light is either on or off, then to predict its next state, we begin with its current state. Let an be the event that the telephone is free at time n. Define xn as the probability of an. So xn is simply the probability that the phone is free after n minutes. Now we ask, how can the phone be free 1 minute later? There are exactly two possible routes. The phone can be free at time n+1 in two mutually exclusive ways. First, it was already free and remains free. The probability that it is free now is xn. The probability that it remains free is 1 minus p. So this route contributes 1 minus p multiplied by xn. Second, the phone was busy and becomes free. The probability that it is busy now is 1 minus xn. The probability of moving from busy to free is q. So this route contributes q times 1 minus xn. Because these two cases cannot happen at the same time, we add them. Therefore, xn plus 1 equals 1 minus p times xn plus q times 1 minus xn. After simplifying, we obtain xn plus 1 equals q plus 1 minus p minus q multiplied by xn. This is the recurrence relation governing the system. Suppose the sequence of probabilities settles to a limit x. If xn approaches x, then xn plus 1 must approach the same value. Substitute this into the recurrence. We obtain x equals q plus 1 minus p minus q multiplied by x. Move the x terms together. This gives p plus q multiplied by x equals q. Therefore, x equals q divided by p plus q. This is the equilibrium probability of the phone being free. It is also called the stationary probability of the free state. We can also find the exact probability at every time n. Subtract the equilibrium value, q divided by p plus q, from both sides of the recurrence. The difference from equilibrium evolves by multiplication with 1 minus p minus q. Define an as xn minus the equilibrium probability. Then an plus 1 equals 1 minus p minus q multiplied by an. This is a geometric sequence. Therefore, an equals 1 minus p minus q raised to the power n multiplied by a 0. Suppose the telephone is initially free. Then x0 equals 1. So A0 equals 1 minus Q divided by P plus Q, which simplifies to P divided by P plus Q. The complete solution is therefore xn equals Q divided by P plus Q plus P divided by P plus Q multiplied by 1 minus P minus Q raised to the power n. Under the usual non-degenerate condition that the absolute value of 1 minus P minus Q is less than 1, the geometric term approaches 0. As n becomes large, the effect of the initial state disappears. Therefore, the probability that the phone is free approaches Q divided by P plus Q. This is the long-run probability of the free state. The mathematics describes a natural physical idea. Initially, we may know exactly where the phone is. But as random transitions accumulate, the system gradually forgets its starting point. The long-term behavior depends only on the balance between becoming busy and becoming free. The probability of being free becomes Q divided by P plus Q. The probability of being busy becomes P divided by P plus Q. The phone continues switching forever, but the long-run proportions remain stable. This stable behavior is called the stationary distribution, or steady state. Consider a numerical example. Suppose a free phone becomes busy with probability 0.2. A busy phone becomes free with probability 0.3. The long-run probability of being free is 0.3 divided by 0.2 plus 0.3. That equals 0.6. So in the long run, the phone is free about 60% of the time. It is busy about 40% of the time. The individual state keeps changing, but the long-run proportions stabilize. Instead of tracking only the probability of being free, we can track both state probabilities. Let xn be the probability of being free and yn the probability of being busy. The next free state probability is 1 minus p times xn plus q times yn. The next busy state probability is p times xn plus 1 minus q times yn. These equations can be written as a matrix multiplication. The transition matrix contains all the information about how the system evolves. Each multiplication updates the probability distribution by one time step. For a two-state system, this may seem unnecessary, but for systems with dozens or thousands of states, the matrix method becomes essential. The same framework appears in many real systems. A weather model may use states such as sunny and rainy. The transition probabilities describe how likely the weather is to change from one day to the next. A customer support agent may be available or busy. A Markov chain can estimate the long-run fraction of time agents are available. An internet server may alternate between idle and busy. Engineers can use its stationary distribution to estimate system load and allocate resources. In finance, a market may be modeled using two regimes, a bull market and a bear market. Suppose a bull market remains bullish with probability 0.9 and switches to a bear market with probability 0.1. Suppose a bear market recovers to a bull market with probability 0.3 and remains bearish with probability 0.7. The stationary distribution describes the long-run fraction of time spent in each regime. For these probabilities, the long-run bull market probability is 75%, while the long-run bear market probability is 25%. More sophisticated regime switching models are used to study market risk, asset allocation, and changing volatility. A similar two-state model appears in quantum optics. Consider an atom with a ground state and an excited state. A photon may excite the atom with probability p. An excited atom may emit a photon and return to the ground state with probability q. The long-run probability of being excited is p divided by p plus q. The long-run probability of being in the ground state is q divided by p plus q. These steady-state populations influence observable quantities such as fluorescence intensity, absorption, and emission rates. A Markov chain models a system that moves randomly between states, where the future depends only on the present state. The telephone example shows how to describe transitions, derive a recurrence relation, solve for the probability at time n, and find the stationary distribution. Even though the system continues to change, its long-run proportions become stable. Whether the system is a telephone, the weather, a financial market, an internet server, or a two-level atom, the same underlying mathematics applies.